In the year 1829, a German scientist named Daubernier found a few group of three elements which exhibited similar properties. These groups were called as triads. On arranging these elements in the order of increasing atomic masses, it was observed that the masses of the middle element is equal to the average of masses of the other two. For example, in the first triad, atomic mass of the middle element sodium is equal to the average of atomic masses of lithium and potassium. Similarly, in the second triad, atomic mass of strontium is equal to average of atomic masses of calcium and barium. Similarly, third triad is formed by chlorine, bromine and iodine. He could identify only a few triads and not all elements having similar properties followed this rule. John Newlands, an English scientist, arranged elements from hydrogen to thorium, that is 56th element known at that point in the order of increasing atomic masses. He found that eighth element had a property similar to that of the first. Like sodium has properties similar to potassium. Magnesium has properties similar to calcium. He compared this trend to the octaves found in the music. Say sa ri ga ma pa da ni. Newland's law held good only till calcium. The properties of the elements discovered later did not fit in the laws of octaves. In order to fit, he put two elements in the same slot. But there were some unlike elements in the same note, like cobalt and nickel, were in the same note as bromine and chlorine, though they are very different. Fe, that is iron, is similar to cobalt and nickel but is in a different note. The main credit for classification of elements must go to Russian scientist Dmitry Mendeleev. Mendeleev created a deck of cards and in each card he represented a different known element. He also included some more information like atomic mass and the ratio in which it combines with oxygen atoms. Let us study these cards and understand what Mendeleev tried to do. We start arranging elements in the increasing order of their atomic masses, starting from lithium to fluorine. Next, we take sodium. We see that sodium and lithium has similar chemical properties, so we place it below lithium. Mendeleev continued this in a similar fashion and ends up with something as shown. Observe Eka aluminium and Eka silicon. These were the elements that were not discovered at that time, but Mendeleev was able to predict their properties. The actual version of this periodic table is shown above. The genius of Mendeleev's periodic table lies in creating space for the elements yet to be discovered. He predicted Eka aluminium should have the mass of 68 grams. It should be a solid metal with low melting point. When it was finally discovered years later by a French scientist who named it gallium, it had the same properties as predicted. Its mass was of 69 grams, it was a solid metal and it had a low melting point. Similarly, germanium and rhenium discovered later had properties exactly as predicted by Mendeleev. Even the properties of technetium, a very unstable element discovered much later, was also predicted correctly by Mendeleev. No fixed position was given to the hydrogen in the periodic table. It acts both like alkali metals and halogens. There was no room for isotopes, which were discovered much later. Like carbon has two isotopes, carbon 12 and carbon 14. In some cases, element in the high atomic mass were placed before the element with low atomic mass. In the year 1930, Henry Moseley showed that the properties of elements depended on their atomic number rather than atomic mass. So how is this modern periodic table constructed? The row in the periodic table is called a period and the columns are called as groups. The elements in the same period share the same number of energy shells. The elements in the first period have one shell, the second have two, and so on. Elements in the fourth period have four shells. The columns are named as groups. Elements in the same group have similar number of electrons in their valence shells, that is the last shell, and these have similar properties. The group number depends how many valence electrons are present. For example, group 17, which has fluorine, has element which has 7 electrons in their outermost shell. If you observe, each of these elements are present in different periods. So if you take chlorine, which is present in group 17 and period 3, it has 3 shells corresponding to period 3 and 7 electrons in its outermost shell. Trends in periodic table. Valency. Valency depends on the number of valence electrons. So all the elements in the same group have same valency. Atomic size. It refers to the radius of atoms. As you go down the group, radius increases. As you go across the period, radius decreases. Metallic and non-metallic properties. This zigzag line of metalloids separate metals and non-metals. Metals are found on the left periodic table and non-metals on the right. Electropositive character. Metals generally tend to lose electrons in a chemical reaction, hence they are called electropositive. As you go down the periodic table, electropositive character increases. As you go left and down the periodic table, electropositive character increases. Electronegative character. Non-metal generally tend to gain an electron in a chemical reaction. Hence, they are called as electronegative. As you go towards the right and up the periodic table, electronegative character increases.